All right. Oops, push something else. I better. Yeah. Okay. Well, most folks survived that last chapter. We're continuing chapter 5, our last section. Hey, we'll finish this chapter next week with a test on Wednesday, day before Thanksgiving. Don't go out of town. Shouldn't, right? Shouldn't. Not supposed to be doing that anyway. And then the week after Thanksgiving is our last week, really dedicated to reviewing, and then the final is scheduled on Wednesday of that last week. Kind of leaves us Thursday in case, you know. Excuse me. All right, so chapter 5, systems of linear equations. Well, there's a term. What does that mean? Systems. The idea here is that, well, last chapter we developed equations that modeled a particular situation. You know, a fixed fee plus an amount to add depending on how many, whatever, hours you worked or something like that. And we came up with equations that describe those situations. Well, the idea here is, what if there are two different sets of conditions that are being considered for a particular situation? What's the value that sort of makes them even out, or what's the value that satisfies both, say, required conditions? So what we're coming up with here are two different equations for a situation, and then we're looking for the point that satisfies both of those equations or both of those conditions. And we're going to see a lot of those, what I call the standard form equations, ax plus by equals c. We're going to see a lot more of those in this section, and still some of the y equals mx plus b equations. And we're going to start today by graphing those equations as lines and looking for their point of intersection. That one point where those two lines cross is going to be that point that makes both equations true. And sometimes they don't cross, and so there's the special cases, right? And then eventually in our next couple sections, we will deal with algebraic techniques for finding that point. Graphing is a visual solution, and we want to be able to do it with just the numbers. So that's what we'll do in the next couple sections. The last section in the chapter is applications, the word problems. I'm going to be trying to mix some of that in little by little all along, so that it's not suddenly here we are at the end and we've got to make up, equations. But get us comfortable with that as we go. Okay, so with that general idea, right? Two equations for a particular situation. And so our first job, like remember beginning of last chapter, we had an equation. We tried to decide whether or not a certain point made that equation true. Plug in the x and the y and see if it makes that equation true. This time we're going to start with two equations at the same time, and then still plug in a point, but we have to plug it into both equations and see if it makes both equations true. All right. So just, sloppy sketch here, what I was just describing is we might have one equation that has a line that looks something like that, and another one that has a line that, whoops, well, let's not put it there, but another one has a line that looks something like that. Where's that point that they share? We're looking for that intersection point right there. That's what we'll be getting to here shortly in terms of graphing. We're not leaving behind what we did last chapter. In fact, we're building on it. And anyway, there's the warning. So systems of equations. We're writing two different equations. So here's a first example, right? And often in this context, you'll see the two different equations grouped together with a brace like that. might forget sometimes, but that's pretty typical format to group them together. There are actually, in the real world, applications of this concept, and really situations where there's more than two equations and more than just two variables. We're not going to concern ourselves with that level of complication, but it happens, right? And there are mathematical techniques for working with those. All right, so the first idea is, okay, I've got these two equations that describe, for some reason, two different situations, two different conditions for our situation, put it that way. And I want to know, is this point, excuse me, 2, -1, is that a solution to the system? A solution now has got to be a point that makes both equations true. So you got to plug it into both of them and test. Okay. So here we go. First equation, and here I do a lot of sort of arrow math here like this. I'm going to plug in 2 for the x and -1 for the y and see what I get. So here I go. 2 minus -1. Does that equal -1? So minus a minus, that's +1, right? 2 + 1. That doesn't equal -1. Right away, I didn't even have to check the second equation. That one's not going to work. That is not a solution. Let's see if they give us one here that does work. All right. So here's another point I'm going to try. So I'm just going to plug this one in here. For that first equation, let's try -4 minus -3. Does that equal -1? Well, minus a negative, that's adding. -4 plus 3. Yep, I got -1 equals -1. Well, good. That point is a solution for that first equation. But I have to check the second equation. All right. I'll try to squeeze it in over here. So 2 times the x minus the y. So 2 times the -4 minus the -3. Does that equal -5? Second equation. So here I get -8. That's plus, right? Plus 3. Yep, -5 equals -5. True. So this one is a solution to the system. Now, unless there's a real special situation, which we'll see eventually, there's only one point where two lines intersect. Right? They're straight. Once they cross, they're going off. So if you've got one solution, that's the solution. That's the one point that's going to make it true. All right. Let's just do it again, okay? And again, like I mentioned, we're going to see a lot of these what I call standard form equations. X's and Y's on both sides. But we will see some, whoops, mx plus b's also. All right, another pair of equations, a system, that's supposed to look like an X there. Test a couple points. How about 1, -3? These are examples from the text. All right, plug it into the first equation. What do I get? 3 times the 1 plus the -3. That's 3 minus 3. 0 equals 0. That works in the first equation. Plug it into the second equation. All right, so 1 plus 2 times -3. Does that equal -5? I get 1 minus 6. Yep, -5 equals -5. That one's a solution. Now, based on what I just said a minute ago, I found a solution. I found the one solution. Unless those are the same line, that's going to be that special condition, then that's going to be the only solution. But, oh, this problem, for some reason, suggested I try 0, 0. I put in 0 for x and 0 for y. Okay. 3 times 0 plus 0, does that equal 0? Oh, well, what do you know? It does, right? 3 times 0 is still 0. How about the second equation? If I put it in the second equation, I get 0 plus 2 times 0. Does that equal -5? Okay, so it worked in one. Now watch out, right? There's the trick. I'm gonna get you. It works in one equation, but not the other. It's got to satisfy both of them. Yep, there goes my frog in my throat. Verifying the solution. That's the phrase we've used before. Plug the point in to both equations and see if it makes both of them true. Yes or no. All right? We'll move on. Here we go. Solving by graphing. All right, so try to present this general idea already. We're going to graph both lines and see where they cross. We get to pick our favorite technique for graphing. Nobody's going to tell you you got to use this or use that, you know, nx plus b or intercepts or whatever, but hopefully we're experts now after the last section. You know, look at an equation and say, oh, this technique works pretty well, or the other, you know. So how about, I got x minus y equals 3, and 2x minus y equals 4. All right, two equations, a system of conditions here. Well, what technique do you want to use? You recall when it was in standard form like this, both of those, we often first look to see if maybe this intercept method would work, where I just plug in 0 for x and see what I get for y, and 0 for y and see what I get for x. You know, I got to pick a couple points, right? I don't see a slope value. Can I just come up with 2 points that I can use to graph this line? Now, sometimes it might be easier to rearrange it and put it in an x plus b shape where I do see a slope and a y-intercept, and I can use that graphing technique. But let's practice this intercept method. Those ones and negative ones are going to divide nicely into 3, and the 2 or the 1 will divide nicely into the 4. So the intercept method should work pretty well. So first equation, I'm just doing this thing, right? If I put in a 0 for x, 0 for x, I get 0 minus y equals 3. All right, negative y is 3, so y must be a -3. There's 1 point on that first graph. All right, just like dealing with just one equation at a time. This was not supposed to look like, this was my calculation, not a 0 for y. What if I put in a 0 for y? Well, then I get x minus 0 equals 3. Oh, x equals 3. 3, 0, there's my other point, another point that I can use. So for the first equation, 0, -3, 1, 2, 3, all right, and 3, 0, 1, 2, 3. All right. Connect the dots. That's just one line. 2 points happen to be solutions for that first equation. All right. I'm going to erase to give myself some room. Okay. And then I'm going to do the same thing with the second equation. All right, so let's try that for the second equation, x and y. If I put in a 0 for x, all right, 2 times 0 minus y equals 4, that's a 0. Negative y equals 4, so y is -4. If I do this too fast, you know, you don't understand how I got there. Not showing every little work step, let me know. Okay? All right, so 0, -4 is 1 point. Let's put in a 0 for the y. If I do that, I get 2x minus 0 equals 4. So that's a 0. I get 2x equals 4. Divide by 2, I get x equals 2. And make sure that makes sense to you. But there are 2 points that are solutions to the second equation. All right? Notice it has nothing to do with the other points I found in that first equation for now. You know, sometimes you get lucky and, oh, I found the same point, but not usually. 0, -4, no, down here. And 2, 0, oh, right up there. Okay, and so now I'm going to draw my line. Yeah. So there is a picture of those 2 equations of that system. What is the point of intersection? Where do those 2 lines cross? This is a solution to both equations. It's a point on both lines, right? Well, now I just got to read the graph. And it looks like I went over 1 and down 2. 1, -2. I could always verify that if I wasn't sure. And if you're using graph paper at home, if you graph very neatly, of course, these are going to show up. You know, they should look like nice integer values on your graph. The weakness, as always, of the graphing technique is if it doesn't line up right on some grid crossing, you're dealing with fractions and you're kind of guessing what those numbers would be. That's why we're going to need some algebraic techniques eventually. But let's see. 1 minus a -2, could it be 1 plus 2 is 3? Or put in a 1, I get 2 minus a minus is 2 plus 2, gets me a 4. So yes, it would make both of those true. This is the basis of what we're doing in this chapter, graphing. See where they cross. We're going to get to some, you know, the special ones eventually here. Different techniques, right? Slightly different looking equations every time here. Let me erase over there, all right? So, standard form, go ahead and take a look and see if that intercept method will work nicely. I won't get any fractions if I put in a 0 for both. You know, that works pretty nice. How about one of these, huh? Y equals 3/2 x plus 1, and y equals -1/2 x plus 5. Well, there are 2 y equals mx plus b shapes, right? So, excuse me. If it's in this shape, I could build a table of values just like I did, but hopefully that slope and y-intercept technique that we used in the last chapter, you're comfortable enough with that. I think that's a faster way to graph this. For instance, for this first line, I have a y-intercept of 1. Oh, I just have to say it was so unfortunate. I gave you partial credit, but on the test, many of you just wrote 1 instead of the instructions said ordered pair. I tried to drill that in. You got to write the ordered pair 0, 1. Oh well, moving on. The number there is a 1. Yes, 0, 1 is the ordered pair, is the point. But let's use our slope now to find a second point. Up 3 and over 2. From that one, a starting point. 1, 2, 3, over 2. Step in front here to get a decent location. All right. There's 2 points for the first equation. There we go. First equation. Same technique ought to work for the second one. How about 0, 5 for that y-intercept? 1, 2, 3, 4, 5. And my slope is -1/2. How about, I'll go -1 over 2. All right? I'll go down 1 over 2. So if I go down 1 and over 2, oh, I think that one's getting me to that same point. I just happen to have graphed, and I'm checking my notes to make sure I work that out neatly enough on my whiteboard here. That just happened to be a second point that we found when graphing the first equation. But that's that point of intersection. What did I get? 2, 4. There's the solution, satisfies both equations. Let's do that again, okay? Y equals x minus 2. Y equals negative 3x plus 2. Get rid of this. All right. Again, mx plus b shape. So I'm going to use the intercept and slope. Now this one has an intercept of 0, negative 2. The slope value we don't really see is a 1, right? 1 times x. Up 1 over 1. So up 1 over 1. Second point. Do them one at a time, right? I've seen all kinds of stuff. Graph your lines one line at a time. And looks like maybe I didn't do that one real neatly, but okay, the other one, let's see. Y-intercept 0, positive 2. And a slope of negative 3, right? How about negative 3 over 1? So down 3 from my starting point, right? Down 3 and over 1. 1, 2, 3 and over 1. Okay. We've seen that point before. 2 points for that line. What's the coordinates? What are the coordinates there? It looks like 1, negative 1. Check my notes here. Yeah. I got that drawn out on my graph paper notes, but I'll make sure I did it well enough on the whiteboard to get the right solution. Again, I wasn't quite sure I could plug it in and verify. Next example. Okay. All right, this one's mixing it up a bit. Remember that kind? No X's. Last chapter, I called it one of those special ones, right? Y is always negative 1. Y is always negative 1. That reminds me, I learned something about mom from your test. Excuse me. Here we go. Y is always negative 1. And I'll just stick another one in there just to give me a good second point. Again, I went back into mom and gave you credit, full credit. But a quirk in mom, when you're graphing a line, it wants you to use 2 points for the graphing. Some of you, at least one person, like it was a horizontal line problem, and I put in like 6 points on the graph and then connected the line. And so mom thinks you're doing more than one line, and it started deducting points. Like somebody had a perfect horizontal line, it was supposed to be 8 points, and they gave them 1.5 points. Wait a minute. So don't worry, I'll fix it for you. You know, I see that, but just like I say, a quirk in the way mom works. 2 points, please. All right, y equals negative 1, a horizontal line, right? There it is, a horizontal line. This other one, oh, standard form. A 1 and a 3 works pretty well. If that's 6, I'm going to use the intercept method. So you can, this wouldn't be too tough to say subtract the x and divide by 3 and put in mx plus b shape. Right? Negative 1/3 x plus 2 or something like that. You could graph it that way. But this is a good one to be comfortable with in this section, using the intercept method. But, excuse me, I put in a 0 for x, right? Here's where I can do my cover up here. 0 for x means I get 3y equals 6. So dividing by the 3, I get a y equals 2. So we get 0, 2 for that one. If I put in a 0 for the y, all right, that one goes away and I just get x equals 6. Hope that makes sense, okay? So this is my second line. 6, 0, 1, 2, 3, 4, 5, 6 is my x-intercept. And 0, 2, y-intercept. Uh-oh. Need to stretch out my bottom graph, don't I? And so that line looks like that. And you can see they're going to cross eventually, so I got to squeeze it into my board here. Now, 1, 2, 3, 4, 5, 6. I did this one. Oh, it is. Okay. So it's way out here. All right. 6, 7, 8, 9. Negative 1. What solution? Negative 1 y value, right? Good enough. 9 plus 3 times negative 1. 9 minus 3. Yep, got a 6. The solution. Double check. Looking at my next line. Okay? Horizontal. We could get a vertical line in our systems too, right? X equals something. All right, so hard to look at my, yeah. Again, kind of mix it up to different forms, an mx plus b and a standard form. So I'm going to use slope and intercept on my first one, negative 1/4 x plus 2. Intercept of 2. And how about down 1 over 4 for negative 1/4? Down 1 and over 4, a point there. All right, well, okay. The intercept method worked pretty well for that one again. Most of them. Not all. A lot of them are going to work out nicely using the intercept form. If x is a 0, I just do that and say 4y is negative 8, so y must be negative 2. Okay. If y is a 0, I just say, oh, that meant that one's a 0. So I get x equals negative 8. Two points for that second equation. 0, negative 2. And negative 8, 0. See if I get enough points on my graph here. 1, 2, 3, 4, 5, 6, 7, just enough. What's going on? I think they look like parallel lines. Right? In fact, if I solve this for y, right? If I solved it for y, subtract the x. Don't use your x, please. If I divide by 4, y equals negative 1/4 x minus 2. Look at that, same slopes. Those are two parallel lines. Sort of definition of parallel lines. They never intersect. They never cross. No solution. You're done. Okay. Special one, right? Special number 1. So, like I maybe kind of said when we were working with parallel lines in the last chapter, they kind of try to hide it. This was mx plus b and this was standard form, so it wasn't immediately obvious that they had the same slopes. Now solving it for y, I got same slopes and different intercepts. So I can see they are two separate lines, but parallel. Okay. Two separate lines, but parallel. And I think there's one double check here. Well, we're going to use some terminology put it that way. Yeah. All right, there we go. Another one. Y equals 1/2 x minus 4, where 2x minus 4y equals 16. Let's graph them. Intercept of 0, negative 4. 1, 2, 3, 4. Slope of 1/2. Up 1 over 2. Rise up to 1. Up 1 over 2. I'll get a point over there. Okay. And all right, standard form. Oh, again, intercepts will work nicely. 2 and 4 divide into 16. If x is 0, I get negative 4y equals 16. So y divided by negative 4, I get negative 4. So what I get? 0, negative 4. If y is 0, right, that one goes away and I get 2x equals 16. Divide by 2, I get x equals 8. 2 points for that one. 0, negative 4. 1, 2, oh, okay, just happens to be that point over there. 8, 0. 1, 2, 3, 4, 5, 6, 7, 8. I have to cheat. That first one is a little crooked through my dots. My dots are too fat. Here, there we go, I'm cheating. Same line. Those two equations are different versions of the same line. Again, if I were to solve for y, I subtract the x's, negative 4y equals negative 2x plus 16. Dividing both everything by negative 4, y equals Negative divided by negative, I get 2/4 x minus 4, which is 1/2 x minus 4. Oh, look at those are the same equations. Again, they were sort of hidden from you, but it's the same condition, the same one condition. Any value that makes the first equation true is going to make the second equation true, and that whole line represents an infinite number of solutions. Infinite solutions. All right, any point that makes one, it's the same equation, same line, infinite number of solutions. So here we are. That's the other, what I call it, the unusual, the weird one, right? There's the other special case. So, which leads us to those kinds of questions they're going to ask you. How many solutions to this system? Right? All right, Race? How many solutions to the system? Well, if they cross one point, there's going to be one solution. Here's my abbreviation, SOL, okay? If they're parallel lines, no solutions. And if they're the same line, we have an infinite number of solutions. 3 possibilities. This one's going to be the most common one, right? But it could happen. There's others. So some of these problems were going to be phrased, I think, eventually as determine how many solutions there are to this system without graphing. No, I got to play around with just the equations and see if they look the same or really different, or same slope with different intercepts, which would be parallel, right? Same slopes with different intercepts, same line, really different. All you got to do here is have slightly different slope, and they're different lines, and they're going to cross some slightly different slopes. Now, we do have some other terminology, unfortunately, right? Vocabulary that we use for these. And one term is, we say it's a consistent system has at least one solution. All right, a consistent system is one that has at least one solution. One solution, consistent. No solution, not consistent. At least one? Yeah, a whole bunch. This one's also consistent. What do we call this one? Well, what's the negative? What's the opposite? Inconsistent. That's kind of how that one has a pretty negative, usual connotation. Inconsistent, so negative. Oh, that's the no solution. Okay, so we can classify these systems. Hopefully, I'm not getting too messy here for you. All right, then the other term that gets used is whether or not these lines are very separate from each other and distinct, or are they the same line? And if they are separate, we say they are independent. Independent, yeah. Separate lines, okay? Independent. If they're not independent, we say they're dependent. Same line. That's the one that's the same line. So I could look again at these three possibilities and say, yeah, those are two separate, distinct lines. This one is independent. Independent. Pretty good if I slow myself down spelling. These two, they're very independent, right? They don't ever even touch. Very independent, although there's no solution, right? Independent. These aren't independent. They're the same line. These are dependent. So unfortunately for these two different classification terms, you know, they don't pair up all the way down through the classification. What you will see, I think, in MOM, unfortunately, I wish it would ask you to use both terms. Like, well, if I say it's inconsistent, there's only one that's inconsistent. If I say inconsistent, I know I'm talking about the parallel. Right? It's one term that describes the different one, the one that's unusual. And if they're the same line, they're dependent. So that's the one term that describes the different one. So, you know, if a multiple choice menu gives, you know, these, you know, is it inconsistent or is it dependent? Well, those are two different conditions, but they really describe one over the other. So these two terms, rather than the pairs of choices, which I would usually do on a written test, fill in both blanks. I think Mom might ask you for one or the other. All right, how am I doing here? Pretty good. All right, time. All right. That's the gist of the technique for solving by graphing. Now we're going to graph both lines, see if and where they intersect. It's okay. Get all that mess here. Let's talk about possible applications. All right, start thinking about the word problems right away, huh? So I'm going to try to pose some situations. You see if you can get ahead of me and write the equation. All right. Whoops. Let's say a manufacturing company is developing a new product. All right. And so the development, it costs them $2,000 to develop the product. And let's say $3 to make each one. Can you write me a y equals mx plus b equation that describes the cost of manufacturing? What I've tried to give you there is a fixed amount that they spent to develop, and then it costs them a certain amount every one they make. All right, cost equals this stuff. You could do b plus mx or mx plus b. You might see it both ways, you recall. But here, so I'll do it backwards. It costs them $2,000 to make it, plus, or to develop it, excuse me, plus $3 for every one they make. There's an equation that you want to be able to come up with. You're building a system. What's the second condition? Well, how many do they have to sell? That's what it's going to come down. How many would they have to sell depending on what they charge in order to get their money back or start making a profit, you know? So the second equation would be a revenue. They charge $10 each. They charge $10 each to sell it. Okay, the right equation? What equation describes that? For everyone they make, they make $10. How much do they make if they sell 0? 0. That's my y-intercept is a 0, which is, I'm not going to see it in my equation. There's my revenue equation, $10 for every one they sell. Those two would go together and make a system. Now we're going to deal with, I'm just trying to get us to think about writing equations right now. We'll find various ways to solve them. I could try to graph it, but 2003, that'd be tough to graph. There are better ways of algebraic, actually. So, but a possible situation where we develop two different equations for this situation, and then we're going to look for that break-even point, right? Oh, $2,000 plus 3x, but here's 10x. But if they sell 0, 0, so that one's going like that. Oh, they got to sell this many before they start making profit. That's a real-world situation. Another possibility. A couple taxi companies, right? I don't know. Everybody uses Uber or Lyft. I've never done any of that. Oh well. One company charges $2.50 per mile. Taxi 1. Okay. Sorry, messy. Taxi company 2 charges $4 plus $2 a mile. I showed up, you got to charge me $4 to start. Two different equations. Can you write, what's my cost? The cost for number 1 and the cost for number 2. Based on how many miles I go. Right. Can you write a equation that describes how much that one would cost me? Let's say we use X for the number of miles. It's $2.50 per mile, nothing extra. This one's just going to be 2.5x. Dropping to 0 there. Kind of like that revenue one, real simple. If I don't drive anywhere, it doesn't cost me. Let's just sit and chat. Taxi company 2, though, I think this is really more like the real thing. You get in the cab and you're already charged $4 fixed, but now it's going to be only $2 for every mile. Which one's a better deal? Depends on how many miles you drive. Again, we're not going to get that picky, but this one 2.5. And this one's you start at 4, but it's only 2, and I'll just say, oh. So if I go that many miles, that cost me the same. If I go less than that many, I think I want to use the lower line, right? That one's going to be cheaper, dollars on this, right? But if I'm going to drive a long way, I want to use the one, this is a shallower slope. I've overcome that $4 fixed cost. This kind of thing that it's very, you might say, simple versions, but businesses, work on it, take into account. All right, I think that gets you through the word problem in 5.1. A version of that. All right, I'm out of time, so I'll stop, but I'll keep throwing in some application problems in each section so that by the time we get to the application section, we've been practicing all along. Okay, that's it for today then, folks. And, I'm spending one day on each section, and maybe there's an extra day at the end, depending on our pace here. But, I think it's really worthwhile for you to show up here, or at least for those who can't make it, they'll watch the video. And, okay, so good luck. Send me your questions, and I'll see you tomorrow. Okay?
Thank you, Steve.
You're welcome. Have a nice day.
You too.